Hello, everyone. My name is Megan, and this summer I had the wonderful opportunity to come down to the University of Florida through the summer undergraduate research program, and I worked in the Herbert Ortham College of Engineering. So, I want to start off with a little bit about myself. I am a soon to be senior studying biomedical engineering with a minor in math at the University of Kentucky. In my spare time, I like hanging with my friends and exploring different places. And this summer, we also played a lot of very different and complicated board games, which was very fun. So, this is my lab group that I had the blessing of working with this summer. Dr. S is in the Department of Mechanical and Aerospace Engineering at UF, and she does a lot of work with soft tissue mechanics as well as drug delivery. Pictured here is Dr. S and her graduate students Isabel, Maida, and Rashid, as well as the other surf intern and one of my close friends, Aubrey. My project this summer was assisting in researching and modeling racinoferatoxin, also known as RTX, and its applications in intrathecal drug delivery. So, I want to start off with a bit about the medical relevance of RTX. So, severe pain management remains a challenging issue for patients that are battling advanced cancer. And the current solutions are these very high dose opioids, and those act on the central nervous system and alter the processing of pain signals. But a lot of them have many side effects, including excessive sedation, cognitive impairment, and even tolerance, which all of these reduce the efficacy of the treatments. So there's a strong medical need for a non opioid interventional pain treatment. So this is where RTX comes in. RTX activates the nonsusceptive ion channel, targeting the transient receptor potential valenoid 1 or TRPV1. And this drug is given as a single intrathecal injection. In other words, it's a very hot, potent chemical. In fact, it's the hottest chemical known to man. It's actually 4.5 million times spicier than a jalapeno. And just like spicy things burn the pain receptors on your tongue, it dissolves the pain receptors that are accessed by the spinal canal in this scenario. And we are collaborating with the NIH in the ongoing study of porcine specimens to develop a model illustrating the behavior of this RTX in the intrathecal subarachnoid space after injection. So here's some diagrams on intrathecal anatomy to give you an idea of where this injection is taking place. So in the picture of the transverse section of the vertebra column, you can see the white matter and the gray matter in the circular space, and that is the spinal cord itself. And we are not injecting into the spinal cord, but the area around it. So you can see in blue the subarachnoid space, and that's where the cerebral spinal fluid resides, and that's where our actual injection is taking place. And you can see in the picture to the right of it the relative injection site of where this is happening. We're injecting into the cauda equina, which starts around the L1, L2 vertebra. And then we're tracking how the drug goes up the rest of the spine and hopefully preventing it from going to the brain. So, to represent the cauda equina in the spinal canal, in COMSOL, we adopted a simple cylindrical model, which has been utilized by other drug delivery models for similar analytical studies. And because the lumbar radius is typically between 14.66 and 16.5 millimeters, we chose a middle number of 15 millimeters for our radius. And we chose a height of 50 millimeters because we're just focused on the injection region right now and therefore didn't need to include any geometry representing the chorda canal. And our model only diffuses a few millimeters, so there's no need to model the whole spine just yet. So the module that we're working with deals with a diluted solute in a porous media. And so porosity is the liquid to solid area ratio, we chose a porosity of 0.8 to kind of estimate what the cauda equina looks like. But we estimate this will probably change with the imaging data we get from the NIH. So another parameter that we needed to include was the diffusivity of RTX, which we did find a literature value for it at 25 degrees C, but the body runs at 37 degrees C. So we figured we needed to convert that, and we found it to be 1.664 times 10 to the negative 6 centimeters squared per second. And then the last thing that we did was look for the concentration of injection that they're doing at the NIH, and that is 0.0207 moles per meter cubed. Next, I want to take a look at some of the equations that we are using to compare. First, we have our 1D derived equation. And the reason we can compare this to our 3D model is because our 3D model is symmetrical in all directions. So we can use the 1D derived analytical solution in a semi-infinite media to calculate normalized concentrations along a chosen z-axis at a singular time point, which in our case, we chose the last time point. And then COMSOL is using this equation, and the concentration of interest is calculated using a function of porosity, which is phi, and effective diffusivity with respect to time. So here's kind of a look at our results that we got. In the orange square is the zoomed in version of the bigger cylinder, but just kind of what the diffusivity is looking like as the time is running. So here are the results that we found and we put into a graph through MATLAB. We found the analytical computations for the last time point, validated our output in COMSOL. So COMSOL and our mathematically derived equation are lining up. And we also found that decreasing alpha, which is our porosity multiplier, hindered diffusion in both of those methods. So when we accounted for porosity only, the distribution of the drug in our column decreased, which makes sense because as you account for porosity, the available space in the column for the drug to travel decreases. But we also acknowledge that porosity is not the only mechanism directing dispersion in the spine. So eventually we are going to manipulate the effective diffusivity constant to match interpolated porcine data from the study to predict what the alpha value would be in that case. So some conclusions and next steps. So after we corrected for porosity in our derived solution, comparing our data from the model in COMSOL gave relatively similar data to our actual manual calculations, which is very good. And our model gave a reliable prediction of the diffusion of RTX in the spinal canal. And then continuing forward without the data from the NIH, we're continuing to add sections of the spinal cord with different porosities and different diffusivities. But after we get the imaging data, we're going to segment for a more anatomical geometry. But long term, we hope to actually get the experimental data from the NIH and then have our own experimentally measured RTX diffusivity to add to our model. And then we can predict more accurately RTX diffusion in the cauda equina to better help advanced cancer patients by maybe establishing injection sites and dosages. Finally, I want to acknowledge some people that really helped me this summer and really made my experience here valuable. Of course, Dr. S., I just want to thank her for giving me this project and this opportunity to work with her because it's been very fruitful, and I hope to continue working with her on this through the semester. And I also really want to thank Isabel for working with me and taking her time to help me figure out how to go about this research and just for working together to kind of solve this problem. And I also want to thank Maida for taking her time to help and teach Aubrey and I in the Raman spectroscopy because that has been super valuable to me, and I'm very thankful to have learned how to do that. And finally, I just want to thank Mike and Ashley for really making this experience truly meaningful and valuable for us and just coordinating all the group events and giving us a good taste of what Gainesville might be like in the future.